Alright, we are on slide 21. They give us the mass of our car. They give it as a scientific notation. It's simple to just move the decimal 3 spaces to convert it to a whole number. We know the initial velocity of the car starts at rest, and they give us the final velocity down here at the very end. My final velocity being 3.4. And it says that there are two forces acting on this car. So there's a forward force of thrust or traction, and my number for that is 1,141. We also have a force of friction, a resistive force, of 931 newtons. So we draw our free body diagram showing both of those forces. And so our first step would be to figure out, well, what's the net force acting on the car? So between these two forces, we know that the force traction is going to be the one to win out. And since they're in opposite directions, we're going to subtract those two numbers. And so when I subtract, I get a net force equal to 210 newtons. Now that I have that, now we can start piecing together and try to figure out, well, what's our goal? Our goal is to figure out, well, how far must the car travel to reach this final velocity? Now, as always, we can do this with kinematics. We could use force and mass to find acceleration, and then use the velocity and acceleration to figure out distance. We could do it that way, but this is the energy section, so we're trying to do this using work and energy. So we're going to use the work-energy theorem. We know that the work done on an object is going to cause a change in its kinetic energy. We know the initial kinetic energy of our car is going to be equal to 0 because it starts off with no velocity. We can figure out the final kinetic energy of the car, and that's going to be equal to the change in kinetic energy. And the equation to do so would just be half the mass times the velocity final squared. Notice how we know both of those numbers. We know mass and we know that final velocity. The other equation we have for work is that work is equal to force times distance. The force here being the net force, and the distance being, hey, that's the number we're trying to figure out. So the setup here, what we're going to do is we're going to expand work into its equation, force times displacement, and we're going to do the change in kinetic energy is going to be equal to the final kinetic energy, which is half the mass times the final velocity squared. If we're going to solve for the distance, then we'll move this around, and our equation for displacement is going to come out to be mass times that final velocity squared divided by, and the force is going to go on bottom with the 2. So I'm just moving everything over to F, where that force there is the net force. This is a compound denominator, meaning you have to put parentheses around it or you're going to get the wrong answer. So let's plug in my numbers and see what my answer comes out to. So 2,800 multiplied by 3.4 squared, and then divided by parentheses 2 times my net force being 210. So the answer I get for my displacement is going to come out to 77.07 meters. And that'll be my final answer.